everybody. Go ahead, Constantine.
Con, you're on mute.
This is Constantine Romanos, with Solutions Architect with StepCG. Sorry, folks, I was looking to the mute button.
We all do that. So good morning once again. So let's get started. Like I said, we have a fair amount of content. So you probably know that today is the third session of the 3 that we've had so far. We've covered fabric fundamentals, session 1, fabric and security in session 2, and today we'll cover the advanced concepts. Constantine, why don't you jump in this one and start us off?
Absolutely. Thanks a lot, Jim. So one of the things that we talked about in the earlier sessions that we did was how with ISIS you have an integrated series of services versus traditionally where it was services that were kind of attached to protocols over time. So for example, ISIS, a widely used protocol by ISPs, runs directly over layer 2 Ethernet. It is encapsulated. It is standards based in terms of that it uses LLDP extensively and TLV type length value fields within LLDP. Very easy to extend. For example, shortest path bridging is an extended ISIS protocol. Right? And it works on an area type of architecture, right? A router is only going to be in one area, and then perhaps the backbone as well. The note here that it says that SPB is currently only defined for use over a single area. I want to point out that actually we now support multi-area as well. So, okay. Oh, there you go.
I'm sorry. Okay, so you mentioned type length values, TLVs. So these are the ones that are somewhat commonly known and used. We break these down so that you can look at the like for example, we covered IP shortcuts in the last couple of sessions here. So 135 would be the well-known for IP reachability, which is the switches that are part of the BEBs and the BCBs both have that IP reachability, and we mentioned in previous sessions that only the ones that actually have it configured on it, the BEBs, would actually see the route tables, where the BCBs would just see the IP reachability. So that's kind of true with all these. So if you're looking to maybe troubleshoot or see what a switch is seeing, you could just use each one of these TLVs and go on from there. This is kind of what they look like if you do a show, ISIS, LSDB, et cetera, and you can get some detail. And we're kind of showing the full detail here without looking at individual. This is kind of show all of them at the same time. So the list can just go on and on and on. So this is kind of a short and sweet slide to kind of show what's going on there.
Hey, thanks, Jim. So talk a little bit about shortest path bridging, or we commonly refer to this as fabric. So ISIS, again, stands for intermediate system to intermediate system, forms adjacencies to neighboring nodes, right? So the network is going to be discovered from a core topology standpoint. Each device maintains a link state database that tells it what is the shortest path to the device to the other device that it wants to reach. And it will use that shortest path methodology or algorithm to make the connection, right? So we're always using shortest path, shortest available path. We're always maintaining a table of the other paths as well. A key point is that there are no paths, there's no blocking involved. It's not like spanning tree where your redundant port will literally get blocked and not pass traffic. We're going to pass traffic on all the ports. We're just only going to use the ones that we need to get to our destination based on the shortest path. Reverse path forward check is the methodology that's used for loop prevention. Our data path is always going to be symmetric because everybody's using the same algorithm. From point A to point B, the shortest path will be the same as it is from point B to point A. So you're not going to get asymmetric data issues, packets arriving out of sequence, and so on and so forth, which can wreak havoc if you're talking about voice communications or video communications, streaming, and so on and so forth. On-demand service multicast for service-specific multicast delivery trees are created automatically. So as a multicast tree is required, multicast handling is built into the fabric backbone infrastructure, and those trees are automatically built. There's no manual configuration of any kind required. IP configuration exists inside the fabric. It is built into the fabric. It is extended that way. So essentially, you get a one big virtual switch.
And that's kind of key. I think if you look at, typical, we'll have used switches in the past, slot 1 to slot 10, for example. This is kind of just like that, but with multiple slots inside there. And just to reiterate what we've said in the past couple sessions, that no IP is really key here. This is not an underlay overlay technology. We totally separate the data plane from the control plane. It's just rise across that control plane, but once again, those switches do not see what the data plane looks like. It just passes through. That's kind of the key with the fabric. So we're going to jump into the data plane and services now. Constantine, why don't you keep going?
Okay, thanks, Jim. So here we're looking at a traditional layer 2 kind of forwarding scenario, right? You have a VLAN 88 on either side of the network, and in order to extend it through the legacy network, you have to do a bunch of configurations. So Jim, if you'd step through for me, I'd greatly appreciate it.
Yeah.
Right. So we're going to make that assumption, right, that we're going to extend this VLAN. We have to add it to all these ports. So the ones on the left, intermediate, and so on and so forth. Right. So when the MAC address needs to send a packet, or the station 0A needs to send a packet to 0E, Jim, if you would.
Sure.
Thank you. No, you're fine. It has to do a MAC lookup table. It has to send it to the first switch, which sends it on to the second switch, which has to do its own MAC lookup to go to the third switch, which has to go to its own MAC table and do a lookup to send it on to the fourth switch. Okay. So those MAC addresses have to be learned on all these nodes in between. Right. So let's move on to layer 2 forwarding in an SPB environment. We have here is what we call cut-through switching, right? MAC 0A needs to send the packet to MAC 0E again, right? And we're going to extend this over a layer 2 service through the network, just like we did in the previous slide. So that we're going to provide the same service. We're going to do it a little bit differently, though, right? And the way that we're going to do it, if you wouldn't mind stepping through for me, Jim.
Sure. Can you? I guess you can't use your mouse to advance them, I guess.
Oh, I guess I could.
Yeah. Try it there.
Is that working? Are we seeing the advancement? I don't think you. I think that's on me.
Are you on Teams or are you in the PowerPoint?
No, I'm in Teams. I'm in Teams. Okay. So VLAN 88, it's called CVLAN here because it is a customer VLAN. But the only ports that are going to be on that VLAN are added on the nodes 8001 and 8008. The intermediate nodes are not going to see that, right? So if you could step through, Jim.
Yeah, sorry.
Oh. All right, and the next one. Thank you very much. So here's an example of the configuration that we're going to do, right? Or we're going to take a look at rather the MAC address. So if we look at the show VLAN MAC address entry 88, you see that we've learned the MAC address, and this is on switch 8001 on the far left. We've learned the MAC address over ISID 10088. And if you remember from previous sessions, we talked about how the VLAN is a traditional legacy construct for the fabric network through the core. Once we get past that initial backbone edge bridge, at that point, we're not talking VLANs anymore. Now we're talking ISIDs because we've mapped the VLAN to the ISID, and the ISID gets automatically connected through the network It's advertised and connected on an on-demand basis, right? So you see, for example, that we are looking at the destination MAC address. We find it on a particular ISID. And if you do the remote MAC table lookup, it tells you the destination, the MAC address 0E is going to be found on destination MAC, and by this it means backbone MAC address, the MAC address of the far end destination switch, 8D is in Delta, and the destination system name is 8008. So we're not having to build these VLANs throughout the entire network. We're really only building them at the edge, and we're only learning MAC addresses where we have to learn them, because the intermediate devices don't care. The intermediate devices don't need to know what the MAC addresses are on the edge of the network, because all they're doing is passing data through from one node to another, rather than one endpoint to another. So note there that no CMACs are going to be learned in the core of the network, CMAC, customer MAC.
Yeah, and just to jump in here real quick, so those CMACs that are learned at the edges, so in this particular example right here, we have what, 4, 8, 9, 10 nodes on the network here. Those 10 nodes would only know the MAC address of other BEBs or BCBs. And in this particular example, the which would be 10 in this example, and then the two switches that we're showing the VLANs on would be only known to those two nodes right there. So they would basically have 11 on both sides there. So we reduced the MAC explosion issue within SBB, because the core nodes don't need to know about every MAC address. The MAC are only known at the edges, and once again, those VLANs are only configured at the edges. So the VLAN is only local significant to the where they're configured, and that ISID is the key there. So jumping into a traditional layer 3 switching. So typical configuration, we get a VLAN on the left, 1200, and a VLAN on the other side, 1200. Typically we couldn't do this, so I'm not sure what this example is showing here, but we're showing IP subnet of 192.168.120 on the left, and 192.168.100 on the right there. So the router is configured. It learns the route, is put into the route table. All the switches in this environment would learn that route. They'd probably be using OSPF or EIGP or BGP or some other routing protocol. So all the routes, all the switches were learned in this environment, so that no matter where that traffic needs to get to, it gets there, based upon the route tables. So assume we want layer 3 connectivity between host A and B. In this environment, we got to configure it, and all the nodes, all the switches here, and once again, it's put into the route table, and provision on it, and then then host A sends a packet to host B, which is on the far side. It gets to the first router. The MAC address is put into the route table along with the MAC, with the IP address, forwarded across to all the different nodes, stripped out though on the far side there, and those two nodes start talking to each other. If we move into the SBB forwarding, as we mentioned in previous sessions, we use IP shortcuts, and IP becomes a cut-through switching environment where we configured a VLAN on the left-hand side there. We configured a VLAN on the right-hand side with the subnets IP. Those two switches, put it into the route tables. The rest of the switches in this example would only have the IP reachability, that 135 TLV. They know where it needs to go to, but they do not see the route table. In this example, we could actually use VLAN 1200 on both sides, and it would not be an issue, because we can actually connect those two VLANs like they're on the same switch. So that's somewhat of an advanced feature set there, advanced concept. Basically, if you had a data center, for example, and you want to put a servers on both sides, and you want to do vMotion, they need to be on the same subnet, same VLAN. We could actually create that VLAN, 1200 both sides, give the same subnet, and give the same ISID, and they would actually communicate across the all these different nodes here. So I like to mention here is it's somewhat like the if you're a Matrix fan, we're actually a new one coming up here shortly. But in the first one, there's that one boy that says there is no spoon. With SPB, we can kind of do all kinds of different things that you can't do in traditional routing or traditional layer 2 forwarding because of how SPB is designed and to work. So there is no spoon. There is no rules that you can't, you can have VLANs talk to other VLANs. VLAN 88 could talk to VLAN 100, for example. Layer 2, just by using the same ISID, because those ISIDs are significant and the VLANs are not. The same thing is true with subnets. We can extend them across the fabric no matter where we need them, and they'll continue to operate like they're in the same switch. Because as Con mentioned, this is really one big switch. So it's kind of like going from slot 1 to slot 10. So really cool stuff. So just building out this slide here, I kind of talked about it already, but walk through host A wants to send a packet to B again, and it puts it in the route table there in the MAC table, and continues across the switches in the middle through IP reachability. Each switch gets passed from switch to switch, and then basically what that switch says, I'm not a part of that zone, that instance, so I don't need to put it to anybody on my switch, so I'm going to pass it on to where it needs to go to, and lo and behold, it gets to the far side. It gets put in the route table on the right, put on the left as well, and both of those nodes start communicating. Constantine, why don't you jump in here?
Absolutely. Thank you very much, Jim. So here we're going to talk now, we're going to extend out the conversation a little bit to talk about layer 2 VSNs and how we use ISIDs to handle multicast trees. As we pointed out earlier, the forward path is going to be congruent. It's going to be symmetrical in both cases for unicast and multicast, right? Forward and reverse. So some important properties to talk about, and Jim, if you wouldn't mind stepping through this for me. All the traffic types use the same path. No out of order packets are possible because of that. Multicast trees are routed at the source node with every service instance and only flood packets to ISID service node members. So basically only who wants it, needs it, gets it, right? Key point, and we've been talking about this a lot for these sessions, is that there's no MAC learning and there's no flooding at the core, which means that your MAC address tables are not going to go insane. You're not going to have to know the location of every node on the network, because SPB is handled to be very economical in how it handles MAC learning, right? So Jim, if you wouldn't mind, so if you'll notice here, your unicast path, your source, your multicast path are going to take the same path. Okay. So moving along, as we said, all traffic types go the same way, and in fact, if you they're doing a really nice job here of pointing out what happens if you potentially lose a link, how the path will adjust. So if you could step through for me, Jim. Thank you. So you see you going VLAN 20, 20, and VLAN 20 at the 3 different nodes, how the traffic is going to go, and again, symmetrical. Okay. Right. So a little bit more about the multicast trees. In this instance, we see a multicast stream that's going to be sourced at one backbone edge bridge, and it's going to basically terminate at 3 other backbone edge bridges. And you see the path that it's going to take in this example. Okay, so that's your multicast tree. If you feel like counting, we are taking the shortest path from a metric standpoint, assuming all default metrics here. You can adjust that, but all metrics are by default, all links by default have a metric of 10 in SPB. Okay. So each multicast tree is going to have a unique ISID, plus the BEB and the backbone VLAN that it's rooted on. And it's going to have a unique multicast backbone MAC address allotted. And we do have a formula of how that backbone MAC address is created. Again, it's going to be dynamic, automatic, and unique based on the nickname of the host. Put a 3 in the end, and then add the ISID number in hex at the end of that. So if you could step through for me, Jim. Oh, well, I guess that was it for that slide.
Yes, so guess what? One thing we don't show in this slide, which I don't really like this slide a whole lot, but it's basically showing the layer 2 VSN here. So we're doing using multicast at layer 2. We've I think in the previous session we've shown that we can also do layer 3 virtual service network multicast as well. But what we're not showing here in this slide is that the ISID for the senders, the video source or whatnot, the multicast stream, automatically, we mentioned before that automatically the first sender is going to have an ISID of 16,000,001 assigned to it. We mentioned before that we can use ISIDs from 1 to 16 million for layer 2, layer 3, IP shortcuts, etc. configurations. Multicast starts at 16,000,001 and goes to 16,777,215. So we roughly have 770,000 multicast streams we can use, which I don't think anybody's ever going to need that many, but they're available to be used there. So multicast, as Con mentioned, it's going to take the shortest path always. Layer 2, only the nodes that need to see it or configure with that particular VLAN are going to see that stream because once again, it's done at layer 2. So we kind of talked a lot about different services, and this is kind of a recap of what we covered so far as we get deeper into some of these going forward in today's session. So we mentioned, global routing IP shortcuts. Once again, we showed how the VLAN 13 can talk to VLAN 14 through the different nodes there. Learn at the edges again. We've shown that layer 2 VSN, the next one down there, VLAN 10 can talk to VLAN 10 using ISID 20,010 there. Nothing done on that is BB core, that BCB in the middle there. We've also shown that VLAN 9 can talk to VLAN 19, layer 2 without IP. In that particular scenario, the host behind those switches would actually have the same subnet configured on them, so they can communicate via IP, but the nodes themselves would have no IP address on them. So strictly layer 2. And then in that scenario, VLAN 9 can talk to VLAN 19 because that VLAN is only local significant and is tied together by ISID 20,009. We've also talked about the other way to do routing using L3 virtual service networks. We mentioned in the last session that VSNs can be also known as security nodes or security networks because we totally separate the route tables. So in this particular environment, we show that VLAN 101 up top there in green can talk to VLAN 102, different subnets, using routing, basically using the IP shortcuts at a layer 3 VRF scenario. Using ISID 30,001, they're tied together. Once again, that BCB in the middle is not a part of the route table there. Just using IP reachability passes it through. And then we show that below VRF green there, red there, that VLAN 201 is going to get routed to VLAN 202 using those different subnets. We've also mentioned that VRF green cannot talk to VRF red and vice versa. So once again, true security zones there. And then down at the bottom, I don't think we've actually mentioned this yet, but in a scenario where we have multiple L2 VSNs where we need to get them routed to somewhere, we're showing in the top there that VLAN 11, I guess subnet of the nodes we get a VLAN. Get an IP address of 10.3.11. VLAN 12 gets subnets of the nodes we get assigned to 10.3.12. etc. They get to the switch, the BCB, in this example because it's showing in the middle, but that would actually be a BEB. And so VLAN 11 to 12 gets configured there, and those VLANs, those ISID would get combined and get shipped out through ISID 30,005, so that everybody else in the network could see those subnets and would get routed across the networks. But everything behind that middle switch there, that BEB in the middle there, that yellow one there on the left, he would only see the routes from those two VLANs. And once again, the nodes behind there would just be assigned an IP address. We call that inter-VSN routing. And then these switches on the right would be part of the L3 VSN or IP shortcuts. We could do it either way. So just to continue on here, so we're showing an example, kind of a somewhat of a decent sized sled example here. We're showing that we have multiple ISIDs, multiple instance, multiple routers and switches, all configured with IP shortcuts. So routes would be on each one of these nodes. What we haven't shown is what do we do? How do we get to different zones if we need to get there? We're showing some firewalls here. Kind of recommended way we've actually recommended, because those firewalls can get down in the weeds, get dirty with the policies and whatnot on them, constrain things, and typically in this environment here, we would probably just pass those subnets when they get to the firewalls. It would basically be outbound internet-based traffic, whether it be on there's two different ISIDs, whatnot, but they'd be stretched. But if we could actually, through the firewalls, we'd actually put them back together and combine those ISIDs at a layer 2 scenario, and so the traffic would actually flow both ways. But once again, if we only want the traffic to be outbound on a layer 2, we would actually provision those layer 2 VLANs on the firewalls, given the IP addresses there. The nodes behind them would have the IP address, but no IP addresses on the switches, and they would get sent out to the internet.
Yeah, oh, sorry, if I could, I just wanted to jump in here because in most cases you're going to have a routed connection to a firewall, but there might be instances where you might have a guest network or something like that, that you want to go directly to the firewall, and you can see an advantage here, where because none of your intermediate switches have an IP address on that network, it makes it inherently much more secure. Plus the fact that you're running ISIDs and not VLANs makes it inherently secure as well. So I'll pass it back to you, Jim.
Yeah, so this could be either we're showing IP shortcuts in the air, but it could be a layer 2 as well. So once again, we can constrain and confine those VLANs based upon, or the traffic based upon the firewalls, or we can just let them talk from node to node to node. So pretty in-depth slide here, but if you have more questions about it, please hit us up on this, but we can get deeper into the weeds on it for you. We're showing a segmented layer 3 virtual service network here. Once again, security zone. We're showing a bunch of different ISIDs that are defined at the edges here. Those nodes can all route to each other based upon those ISIDs. We're not showing the VRFs here, but we actually be VRF assigned. We are showing VRFs, but not based upon color. But so 30,010 would be basically a student VRF. 30,009 would be IoT devices, could be a guest network, could be HR, whatever you name the zone. And we're basically showing how each one of these nodes can actually have it defined. Multiple route tables here. They get to the firewall. They can be sent to as outbound traffic to the internet, or routed back through different nodes here based upon the firewall policies, so that the top switches can see the bottom switches. But even before that, the BCBs even the BBs on the right and left would actually transport that traffic to each other based upon their ISIDs. But ISID 30,010 would not see traffic from 30,009 and vice versa. For that traffic to see each other, it would have to go back through the firewalls. But once again, we can keep all this traffic segmented and either sent out to the internet or based upon our firewall policies, sent back to each one of these different ISIDs or VRFs. Anything to add there, Con?
You nailed it, Jim. All righty. So the next few slides, we're going to talk about the different kinds of unis that we're going to use within layer 2 VSNs. And if you remember back to our prior sessions, we talked about the uni as the user to network interface, how we translate user constructs like a VLAN into a fabric construct, which is the ISID, right? Not the VLAN. So the first one we're going to start with is the CVLAN uni, the customer VLAN user to network interface. And this is something that if you're running a fabric network, you're already very familiar with this concept. We map a VLAN to an ISID and transport that through the network, right? So we can say tag traffic, untracked traffic, however it goes. In this instance, if you are in VLAN 12, doesn't matter where you're coming in from, the traffic's going out ISID 3000, 11, 2000, 10, 1000, etc. Right? So from the backbone edge bridge standpoint, the Fabric Connect standpoint, you see the command there, and there's also the command sequence you would use if you're in Fabric attached mode as well, right? So key point, the VLAN's global significance is at the edge, at the BEB or the FA proxy, and layer 2 switching is going to happen on local VLAN port members, transported over layer 2 VSN for the remote endpoints. Okay. So let's go on to the next one, please. So the next one we're going to look at is the flex mode switched uni. So you can hear this called flex uni, you can hear it called switched uni. It's the same concept, right? This gives us a little bit more flexibility, as you may guess from the name, right? Where in a flex uni, switched uni scenario, the VLAN only has local significance on that particular Ethernet port or on that particular MLT. So, and by the way, you can combine the different ones, right? You can say that, as an example, globally, VLAN 10 goes to ISID 10,000, except for, in this case, port 2, in which case VLAN 10 is going to go to ISID 2000 instead. Right, that's why we call it flex, right? Because you can make an exception to the rule for a particular use case. Okay. Situations where you might want to do this is if you are connecting legacy networks, for example, that you might have a VLAN conflict, a VLAN number conflict, where you need to actually match different VLANs for particular functions. You don't have to do it globally, put an entire switch out, say for one user to map to a VLAN. You can do a flex uni to make that connection. Okay. Jim, anything you want to add on this one?
And I was just going to say, I think the kind of the cool part of this is you get that untagged traffic at the edge there, and we can actually assign it to an ISID here and send it on its way across the fabric, unbeknownst to the user at the edge there, right? So, it's kind of cool concept.
Yep. Yeah, very true. And the way that we're doing that, by the way, is if you're coming from an ERS environment where you would call it a PVID, you may know that as a default VLAN, but that's the way we define that, right? We're still assigning a VLAN to untagged traffic, and then we're going to assign that VLAN to an ISID, either globally or specifically based on the particular port that it's coming in on.
Yeah, so lots of flexibility here, and once again, there is no spoon, right?
Right, there is no spoon. All right, so transparent port uni is another really cool feature, and we've been talking a lot through this series about how ISIS came out of a carrier environment. So a lot of times, if you work with different carriers, they might give you a dedicated port, say for a particular remote site. Okay. And they'll tell you, we don't really care what traffic you send through it. It could be tagged, it could be untagged, it could be whatever you want it to be, because we're just going to take all the traffic from one side and we're going to dump it out the other side. Okay, well, how are they doing that? Well, the way they're doing it typically or frequently is by using transparent uni, right? Where we don't care what the traffic is that comes in. All the traffic on this port, in this case, port 1, port 2, and port 1, all the traffic is going to go into ISID 2000, tagged, untagged, voice, video, whatever it is, and it's going to get transported through the network and dumped out the other side in its original format. Again, all queue tagging is going to be respected and maintained. Untagged traffic respected and maintained the same way, right? The port does not even have to be VLAN tag aware, because as soon as you set it as transparent, it's simply going to take all that traffic, dump it into an ISID, make the connection through the network dynamically, and spit it out the other side. And of course, because we're using the same path in both directions, it's going to still be fully symmetrical. It's still going to have all the benefits of Fabric that we've talked about in a fully transparent fashion.
Yeah, so some pretty cool concepts here. So you might be thinking, well, I'm not that big of an organization, whatever. I probably don't need this, but we have a lot of customers actually that use this. For example, we have a number of airports that use SPB, and they have multiple clients on their network, like American Airlines, Frontier, Spirit, you name the airline, right? That need to transport from one terminal to another across the airport's fabric. So this is how they do it. They use a transparent uni, send that traffic across the network. Nobody sees the traffic from end to end. Is hidden, so that client feels comfortable knowing that his traffic's not going to be hacked somewhere in the middle. So kind of cool concept when you think about it. So we're going to talk. We've mentioned Fabric Attach off and on throughout the last couple of sessions, but really haven't gone into what does it really look like, right? So we have some concepts called automated campus, where really you basically set up your network. We're showing somewhat of a large network here. It doesn't really matter the size, but we know that somewhere in the network you're going to have an IDF, a wiring closet somewhere. And what do we do about that if it's not a BEB or a BCB, right? How do we get that traffic onto the fabric? Well, we use Fabric Attach. We use our XOS switches, and as Constantine mentioned, we even have the older legacy VIA switches, ERS switches, that can actually be a part of the Fabric Attach as well. We have APs that are Fabric Attached from Extreme, with our Wing, as well as our XIQ APs are Fabric Attach. So a lot of devices that we can actually Fabric Attach. And Fabric Attach really is nothing more than adding different elements to the switches at the edge here. So the Fabric Attached server would actually be a BEB. And then we have a term called Fabric Attached Proxy. Typically, that's going to be an edge switch where it needs to send some type of Fabric Attach signaling to something behind it, like an AP, for example. So in this particular environment, I would have a FA server being a BEB. I have an FA proxy would be an IDF switch, like an XLOS switch or ERS switch. And then I have some type of client that would be a camera, an AP, some type of device behind it that will actually get the information automatically from it. Kind of the cool thing with Fabric Attach is that the nodes themselves, once we configure the Fabric Attach configurations on it, the nodes themselves would actually be provided with automatic information. So, for example, as we built this slide out here, let me just back up here. So we enable FA server on an SPB node, right? Switch at the edge, and then we add a FA proxy switch, like I mentioned, a wiring closet switch at the access layer there. We tell the switch that he's a part of a VSN or a VLAN with an ISID, and automatically he's already set up to be a fabric attached client or proxy, so he automatically gets his information from the network via IP management, IP address, so automatically put onto the network, automatically assign an IP address from the DHCP server, becomes a part of the management stream there, and automatically already on the network. So everything done dynamically assigned to network there. We add on a user. It could also be, he's not really a fabric attached device there, but at this point in time, we would configure a VLAN for him or assign him to a VSN, and then the way he would go across the network. If we add another switch cluster there, the same thing would happen. Constantine, whatever switch cluster in the last, actually, I'll go over it later on this session here, rather. But if we had a cluster, the switch there on the bottom would actually know it as well. What I'm not really showing here is that typically, if that node that we're showing a laptop there on the right-hand side, if that was a AP, a camera, etc., those type of devices, would automatically get assigned an IP address as well. In this particular example, we'd actually have to provide some type of IP address to the VLAN there on that fabric touch proxy. But we could also use automated campus, where we would actually do everything through a NAC environment there. So here we're showing that camera getting assigned to the VSN and get transport. He would actually get his IP address, his VLAN, etc. This would automatically be assigned via based upon that FA proxy. He'd be attached to the network automatically, and then we would actually, based upon our configurations that would do automatic, he would be assigned to the proper VLAN, and his traffic would start getting seen by whoever needs to see it, example. So that I said for the multicast stream would be automatically assigned. The multicast stream would start, and once again, everything would be automatic in this environment. To do, to get a little more in the weeds here, not to get too deep here, we don't want to do this at a high level, but we can do all this automatically based upon extreme NAC, extreme control. Users at the edges would automatically get assigned their VLANs assigned, their ISIDs assigned at the edge port there on that FA proxy edge port. So automatically attached to the network based upon that extreme control, and plug them in, automatically gets connected via based upon the wired connection. Same thing would be true with an AP. You get attached to the AP based upon your SSID, etc. Automatically get your IP address, get your VLAN assignment, and that FA proxy would have that VLAN based upon an ISID, and your traffic would converse around the network where you need to go. So very, very deep in the weeds here on this one, but we'd love to talk to you further detail on how we actually handle automated campus here. StepCG is really, really good at doing this. So they have a number of their customers that use this technology. Once again, it's hands off for the administrators. Basically, once you configure that control, users come and go. When they unplug, the network goes away. When they plug in or connect to an AP, they get the services they need to get. So automatically they're on the network. Constantine, anything to add there?
Yeah, I was just going to say that there's a whole lot of stuff that we can go into with Fabric Attach, and love to get into it with anybody who's interested in kind of getting the weeds separately from this. So that's about it. Like I said, you could really go down deep.
Yeah, we really can here, but we'll just kind of go through this for the high level for right now.
Right.
So moving on here. Oops. I think I'm moving on here. Here we go. Okay, Constantine, why don't you jump in here?
Fantastic. Thank you, Jim. So we're going to talk about clustering, which Jim mentioned briefly a few minutes ago. Clustering, and you'll probably have this in a lot of your environments, especially if you're doing dual core type things. But what we're doing here is we're creating not only link redundancy, but nodal redundancy, right? So if you look at the dotted line, for example, between BEB1 and BEB2, that's the VIST, it's the virtual IST. So what's that giving us? Well, that's the virtual IST is a link, and we call it virtual because it does run over ISIS, right? So they're not showing, for example, in this diagram, they're not showing you a direct link between BEB1 and BEB2. Normally there would be, but the great thing about it is that if that direct link were for some reason to break, that virtual IST, because it's virtual, because it runs over SPB, would simply get rerouted through the fabric network to make the connection between the two switches, and it would happen in near real time. So what does the IST give us? The IST is the inner switch trunk. So that allows the two nodes in the cluster, the two peers, and peer is an important term that comes up a lot when you're talking about clustering and IST, but it allows the two peers to identify each other, send each other heartbeat information, exchange forwarding tables, and occasionally traffic, but there's going to be minimal traffic traversing the IST. The primary function of it is for heartbeats, keep alives, basically, you there? Yes, I am, and forwarding database information. Key points. Not only are you increasing your resiliency by the fact that you're replicating the two switches, but you're also going to increase your performance because everything's going to pass traffic. This is not an active standby kind of scenario. This is fully active. And we're going to talk a little bit more as we move through as to how that works. So, Jim, do you want to add anything on this one?
No, I think you covered it pretty well there. Just one thing you did mention is that that node, just two BB1 and BB2 there, they use that part of the virtual IST as an ISID, which is why we can actually transport it around the rest of the network there. So if that link breaks, like you mentioned, it gets used. The ISID get used to transport it to the BCBs and then back to BEB2. So that's kind of the key there, is that ISID kind of links them together in the virtual IST world.
Yeah, very, very good point, right? And that's why we say that they don't have to be directly connected, but of course, ideally they would be, but there's a backup path.
Correct. So, yeah, we would actually have that link there. Yes.
Right. So, all right, let's move on to the next one, please.
So this is the next slide here.
Oh, there's the next slide. See, it just looks so similar.
Snuck it in there on you. Sorry.
So the virtual IST's been supported since VOS code 4X. We're now on 8.4, so it's been around for quite some time. If you came out of a legacy Nortel Avaya environment, you would have known it as just the IST back then, because it wasn't virtualized at the time. It had to be a direct link between the two switches. But again, virtualizing it has given us a lot more flexibility and reliability in the cluster. A couple of points about this. Whereas previously with the physical IST, the switches had to be identical. That's no longer the case. The virtual IST, you can actually mix the models. So you can have an 8K and a 4K as an example, a VSP 8K and a VSP 4K, backing each other up and providing those services. We don't typically do that, but if for some reason you needed to, you could, right? As it says, no longer requires a multi-link trunk between the cluster switches. And again, that is true. That is no longer a requirement, but as we stated, you probably would want to have that so that you do have that, the true shortest path is a direct line, right? But as long as you've got SPBM connectivity between the peers, the IST is going to stay up. Okay? As far as configuring it, there are a few configuration steps involved, as you would imagine. And but it's very straightforward. You create a layer 2 VSN, so a VLAN again with an added IP address. Typically, you would use the same VLAN number across all of your VIST pairs. So if you have a VIST pair, a cluster, say at a distribution layer at a particular school, you would use VLAN, typically we use VLAN 4053 to create the connection on all of them, right? So every time you have a pair, we would use the same VLAN. And how can we get away with that? Well, we can get away with it because, again, ISIS and shortest path bridging rules apply, where the VLAN only has local significance. What really matters to the fabric is the ISID, right? And so that's how that comes into play. We do have certain parameters that we have to add. Some of them are going to be unique to the pair. Some of them have to be unique to each member of the pair, and that's that kind of goes through. As we do these build outs and installations, we'll typically create a table that's going to identify all that so that you can, so it's properly documented. But essentially, you have to peer with the peer cluster's IP address and the VLAN and the layer 2 VSN, VLAN ID, and IP address. SPB IP does not need to be enabled on this particular link because it is strictly a layer 2 link. So you don't need to include it in the GRT. A couple of points: you cannot assign edge VLANs to an IST, and you wouldn't want to, because again, the IST is only for switch-to-switch communication. If they need to pass traffic through, actual user traffic through, they can still do that, but they will do it in their own way. You don't need to do it any manual configuration there. You do have to assign an ISID to it, and there used to be a feature called an SMLT ID, and that's no longer required there. So, okay.
Yeah, just to add on there a little bit. So like you mentioned, Nortel and Avaya back in those days, pre-SPB, those two switches were tied together with a could be an MLT and multiple links, whatever, but typically at least a single link there. If that link died, we had the split brain scenario. I'm not sure if we mentioned, but each one of these nodes in this example, even right here, they learn each other's route tables, they learn each other's forwarding database, MAC address, etc. So they act as one, as a single switch. So you can really just draw this as one switch in the middle, talking to a switch on the right there. But so those two switches act as one. Pre-SPB, if that link broke, you'd have a split brain issue where the traffic would get screwed up in a hurry because of that route table. They would learn different routes and traffic wouldn't get back and things like that. So all kinds of things would happen in that environment. With SPB, because of the ISID, that link can break and it'll find the next path, the next shortest path to get back to that node again. So kind of cool. SMLT there on the right hand side with that uni there. This is basically just an IDF switch, somewhere. We can, it can use everything we've talked about already: fabric attach, ISIDs at the edges on the switches, edge configuration, etc. Nothing changes on there except for now we have redundancy built in so that no matter what happens on that edge switch there, a link breaks, it's still going to get back to a core somewhere, and the traffic gets traverse the rest of the network. So kind of cool feature set here with this. So a way to build in additional redundancy.
Yep, very good. And one thing that I did want to add on this is that that SMLT uni, that could be going to anything, right? So if you, for example, you could use a pair of VSPs, well, VOS switches, really, not necessarily even VSPs. It could be the Universal series to support servers in the edge and dual home them and give them that same advantage in terms of throughput and resiliency that you could have at the stack edge as well.
Mm-hmm.
Very good. So
I'm going to build this out for you.
Yeah, that's great. Thank you very much. Appreciate that. So some recommended settings. gateway redundancy, that's obviously going to be an issue, because if you're doing it at layer 2, well, you want to make sure that you've got redundancy at layer 3 as well, right? So we can support either VRRP, which has been enhanced with a backup master enhancement that allows us to do active VRRP versus active passive VRRP, which is a big thing. We can also do routed split multi-link trunking, which is typically the way that we do it. It is it's a cleaner implementation than VRRP is, but we could realistically do either one. Simple loop prevention protocol, and that's something that we certainly want to have enabled throughout the networks, but they prevent the loops in the switch cluster networks. If it happens to notice a loop on an uplink port, it'll disable that port, and that's a important thing, because if you somehow have a loop generated at the edge, you don't want that. If you have the loop generated outside the fabric network, right? Because we've talked about how fabric handles loops its own way, right? But you certainly want to make sure that you don't have those loops at the edge, and you have a way to trap them and prevent them. And you definitely don't want SLPP on the IST. That is an inner switch trunk. You want that traffic to pass through cleanly. So that's one of your recommended settings. And VLACP is another one. VLACP gives you an end-to-end health check. And the advantage of it is that if you're simply relying on layer 1 for your health check, right? Do I have light on that fiber, or do I have link on that copper link? That might give a false positive, right? That a link is up doesn't necessarily mean that the switch is up, right? It just means that you've got electrical signal and you're passing it. But VLACP gives you a layer of intelligence above that, which allows you to have that end-to-end health check to make sure that before we bring up that link and start passing traffic through it, there actually is a device that's fully operational on the other side and configured and ready to pass traffic. And this allows us to detect end-to-end failures rather than just point-to-point failures. Okay. One thing I would point out is VLACP stands for Virtual LACP. LACP stands for Link Aggregation Control Protocol. I don't know why they chose this name, because VLACP is not an extension of LACP. It is not an aggregation protocol. It is simply an end-to-end health check protocol.
Yeah, it's a good point. Very good point. Yeah.
So a great feature, lousy name. Confusing.
Yeah, for sure. So we're running a little bit short on time here. So we have a bunch of things. So basically, Constantine mentioned RSMLT, how we would actually do that sub-second failover at the edge there. Once again, these switches all act as one there. So we what we've covered so far today is like, we probably should have covered this in a 2-hour session, but so some of the things we could have went way deeper into, but we try to give you as much advanced concepts as we can. One of the things left here in the last minute or so, our CFM connectivity fault management section here. Just a real quick couple slides here, but how do you test the traffic from end to end? Well, with SPB, we can actually do a layer 2 ping. We can do a layer 2 trace route. Once again, because those nodes in the middle aren't a part of a network that BCB, they don't see that traffic. We can actually do that end to end, do an L2 ping, so pinged nodes on the ends and whatnot, things like that. We can do a layer 2 trace tree to tell me exactly how it goes from switch 1 through switch 3 there in this example. So all the nodes it sees along the way, so I know exactly how it's getting there. And if something changes later on, I would know how that changes as well. And then L2 trace multicast routes. How does my multicast get from end to end? Basically, because that ISET is automatically assigned, as we mentioned. So a lot of key concepts there. That layer 2 trace route there. Once again, it kind of we've all used layer 2 I'm sorry, layer 3 pings here in this one here, the example here. We've all done pings and trace routes, but we can do this layer 2. I think I mentioned earlier that we do a trace route, node 1, all the nodes in the middle wouldn't see, so it would basically be one hop on and one hop off again there. So kind of cool. We don't lose the layer 3 stuff that we were familiar with, but we give you some additional ways to test the network. So with that, we're going to kind of end the session for today. We're right at the top of the hour, but so Michelle, I don't know if we have any questions or even time for questions, but we want to thank everybody for attending this webinar. If there's questions out there, we'll get back to you with those answers. But once again, we want to thank each one of you for joining the session here, and we've enjoyed presenting to you, et cetera. Constantine, anything to add as we wrap up here?
No, I sure don't. Thanks a lot, Jim, and just wanted to thank everybody for joining us for the series of webinars. It's been great, and we look forward to having more conversations with you about the things that we've talked about.
Absolutely. And yeah, if anybody has any questions, we don't have any in the chat, but feel free to email any of us, and anybody can follow up with you.
Perfect. Thanks, guys. Take care.
Thank you. Everybody have a great holiday season.
Thanks, everybody. Bye-bye now.